everybody. I'm Amanda Kaminsky, and I also, just relevant to the topic of conversation today, sit on a couple of boards, one of which is the Carbon Leadership Forum, and the other, the Health Product Declaration Collaborative. So relevant to some of what I'm going to be talking about today. These are just some of the basic topics I'm going to cover. I'm only going to be talking for about 15 minutes, but wanted to really put some of the embodied carbon conversation into the context of other issues that we're looking at on a regular basis with, our materials purchasing, our equipment purchasing, because there's a lot of topics of focus that we've been looking at for a long time in that procurement over many years. I just joined Lendlease in February, so am delving into all of our projects and getting familiar with them. I'm a bit more familiar with our New York projects than some of the others across the U.S. I'm trying to check off the boxes of getting to see all of them, but they're constantly evolving. And we have different opportunities with each of these projects. Sometimes we're third-party construction managers. Sometimes we are playing a design build role. In other cases, we are the developer and the builder. And in some rare cases where we don't have the folks on the ground, we sometimes just develop and hire a third-party builder, though that's pretty rare. So I'm going to talk a little bit about planetary boundaries, not a whole lot because that was covered really well earlier with regard to tipping points, a little bit about whole system material health, and some of the different scales and impacts on that front. And then a little bit about what we're doing right now. Super excited about a lot of what's been broached here today. And it's some of these materials and techniques we've been looking into and starting to look at the possibility of piloting here and there. Sometimes we are a bit constrained with some of our building codes, and so we're also looking into how we partner with different municipalities to evolve those as needed over time. So I like this graphic and its evolution over time. It's nice and neat, and it's neater than it is in reality for sure. But the Stockholm Resilience Center, I believe, started publishing this about 12 or 13 years ago. But I just want to draw attention in particular to the novel entities, which is a synonym for chemical pollution and climate change. And those are the two that I'm going to be mostly focused on today. But we have, there's been a few reports and articles over the last couple of years, especially just in particular talking about plastic pollution. And there's a lot of synergies, I think, between these two. So when we reduce chemical pollution, very frequently, we also are reducing climate impacts and vice versa. So I think sometimes in the built environment, there's trends, and sometimes there can be a bit of myopia in in those trends, and we do see that happen. Although this group today, I've been really impressed with kind of the big picture outlook on really needing to address across the board all of these considerations. So this is an overhead perspective on Kalundborg in Denmark. And the reason I bring this up is I think about it a lot with regard to really creating no waste. And by waste, I mean no material waste, no energy waste, no water waste. And this is one of the first examples, if not the first example, of industrial symbiosis. And it wasn't mandated. It kind of grew up over time. And you can see here, and you might not be familiar with some of the company names, but it doesn't necessarily matter too much. But you can see the flows here diagrammed between the different companies where any water, energy, or material waste is being uptaken by another company within this system. So I think a long time ago when I used to talk about some of these issues, I put a picture of a natural ecosystem up on the screen, and over time it felt false to me, because so much of the systems that we're working within are a combination of natural and industrial or people made. And so it's I think this is a kind of a beautiful thing. Yes, I believe there's still coal-fired power in this system, which is imperfect, but I think that's also something that I face every day, that there is inherently an imperfection to our supply chains, and we're just all trying to make them better and better over time. But this is really I had the privilege to see this in person about 5 years ago, and it's worth seeing. It might not be one of the traditional tourist stops in Denmark, but it's super cool to see in person, and really see the piping and witness how these flows work on the ground. So conversely, right now we're doing a lot to figure out how we electrify better over time, and that inherently is involving energy storage. And so recently we've been looking a lot at how do we electrify our job sites better and at larger scale. And so we've been looking at larger energy storage battery units. And the traditional, in order to really maintain as small a footprint as possible, lithium-ion batteries are really, the most efficient on that front right now as far as what you can actually buy. However, in looking into this over the last number of months, there's, first of all, if you can even get a lithium-ion battery, there's a lot of baggage that comes along with that if you wanted to see it. And so there's where the lithium and the cobalt is mined. This is actually in some ways, in the abstract, kind of a beautiful image. But if you look at what the impacts on the ground are, they're not great. There's a lot of impacts to the soil, to the air, and there's people that live not far from here. Further, when we look at how where those materials then travel to actually get made into the units that are the batteries that we buy, there's a lot that is happening in a black box that we're unable to really understand in sufficient detail to gain alignment with that. So we're looking a lot at what are some other options for batteries? What are other technologies? One of those is a zinc manganese dioxide battery that we haven't fully vetted yet, but we're, is looking a lot better on a number of these fronts, and there's a lot greater transparency into its manufacturing. So it's just been a caution for us internally that, it's not just about moving away from fossil fuels and just to electrification, but you can encounter a lot of similar troubles if we're not careful in how we go down that path. So speaking of paths, this is our at Lendlease, our Mission Zero roadmap. So we have the goal of 2025 being net zero carbon, which we've reached already a bit early, and then this is the tougher one, the absolute zero by 2040. So this is specific, I should note, to our construction portfolio that I oversee here. And we have achieved this through the purchase of carbon offsets in part. And there is traditionality to those carbon offsets that we've vetted. It's mostly a wind farm in Oklahoma, but that's very abstract to our folks on the ground, and it's it's not yet been possible to make all these other things happen, and so that was the way that we could get there right now. But I spend a lot of my time every day focused on that 2040 target, and I'm not going to get a whole lot into the fuels and the power today, but I am going to talk more about the embodied carbon, and I'm mostly going to be talking about what we're doing right now. In the time that I have today. But one of my favorite things is to think about what we can also be doing in 3 to 5 years with some of these materials. So you can see here, I will be talking about some of the specific materials that we're working with to lower embodied carbon. And then specifically about some of what we're doing on job sites to reduce waste because of the impact that that also does have on reducing embodied carbon and being careful with our resources. So we are consistently looking at building reuse right now on the whole, and then also some of the internal components. We're working with Sean Regal actually on the collection of a bunch of doors out of a building that I can't say a whole lot more about right now. It's a project in process that's on a temporary hold, starting again next year. But there's quite a lot of doors in that building that are in very good shape. And Sean from Carpet Cycle is going to be helping us with the removal of those doors and routing them to a company in Pennsylvania called Doors Unhinged that actually refurbishes those and repurposes them into new uses, mostly new doors. This is a lot of words, but a few years back was looking at helping our teams understand how to not miss some of these really important milestones, especially in the contracting, design, and permitting stages for who needs to be involved when, in order to make sure that deconstruction remains an opportunity that's actually viable to the fullest extent, and the reuse that it affords. So this was just a timeline that we put together at that point. With regard to remanufacturing some of the materials that we pull from our jobs, the gypsum drywall, first of all, there's a lot of it on a lot of projects in our urban centers, especially, but really on most projects. And we have traditionally over the last couple of decades gotten a lot of synthetic gypsum from coal-fired power. Because so much coal-fired power is going offline, we are needing other sources of gypsum, ideally not, going back to just mining a whole lot more gypsum. So we've had a lot of interest recently. This is something that we're optimistically predicting, and it's coming true, that a lot of those manufacturers would be much more interested once they couldn't have that source of very cheap synthetic gypsum. So another driver besides just the resource reuse capability and the embodied carbon reduction that goes along with that is that when gypsum goes to landfill, it is a primary cause of hydrogen sulfide gas. And I'm mainly talking about C&D landfills. There's other sources of that cause hydrogen sulfide gas to form in municipal landfills, but C&D landfills, gypsum is usually the primary cause. And hydrogen sulfide gas, doesn't smell good. It's kind of that rotten egg smell, sulfuric smell. But more importantly, it's an asthmagen, and it also causes neurological issues at higher concentrations that are not atypical in landfills. And so, I think a lot of times people don't think about this, don't know about this on a construction site when they have to decide, okay, we're really going to source separate the gypsum. We're going to take up that precious square footage and logistical planning to make this happen. It's another major driver for our teams. So it does take extra planning and careful logistics. We have some great partners in the region. This is Cooper Recycling, who has the capability to receive the drywall source separated so that it doesn't crumble down and turn into fines that are undistinguishable as gypsum and therefore not recyclable. And then this is some folks at Certainteed. They're the only gypsum manufacturer in New York, gypsum wallboard manufacturer in New York. They're in Buchanan. They're the ones that just locally reached out recently because a coal-fired power plant that they were supplying material from or receiving material from West Virginia just went offline this summer, and they're now getting most of their gypsum. I think they were getting in, 98% of their gypsum from that power plant. It's now all coming from Spain. So you can imagine they're quite driven to receive post-consumer recycled materials to offset, the cost and the material shipments in. Again, a lot of words on a screen, but this is another logistics page, just a kind of a cheat sheet that we put together for construction teams a couple years back to help make the logistics planning easier. So these are a number of different scenarios that I've encountered over the years on projects that I've been on for how to source separate, whether you have constraints on each individual floor, at the loading dock, or in the trucking stage of the process. So just to help make it easier. So lower carbon steel, luckily these pictures here are from a plant that is in South Amboy, New Jersey. That plant is an electric arc furnace mill that utilizes 98% scrap metal, which is this is what you see right here when you go visit that plant. Here in the US, a lot of our steel has transitioned to electric arc furnace. We used to use a lot of basic oxygen furnace in the US. Around the world, there still is a lot of basic oxygen furnace production, but there's a huge difference in recycled content and therefore embodied carbon because of the energy involved in that process. So it's 25% on average, maybe 30% recycled content versus electric arc furnace, which is more like upper 90s. So really big difference. So you can see this is kind of the graph of how that's changed over time. This is US specific. So the red is the basic oxygen furnace diminishing. The black is the electric arc furnace increasing. But alongside that, we've all heard a lot and used probably a lot of cement replacements over the years to reduce the impact of our concrete mixes. Slag is it's a byproduct of basic oxygen furnace steel making, iron more specifically. And so the less basic oxygen furnace steel making we have, the less slag we have. So it's a good thing that steel's transitioning to electric arc furnace, but this is just sort of a, it's an alarm that I've just been wanting to make sure everybody is really aware of that. Yeah, cement replacement is a really kind of readily easy way right now to lower the impact of concrete that you do need to be using on any projects that need it. But those cement replacements, the ones that we've been using for a lot of years, are going away. Same thing with fly ash, with coal-fired power diminishing, a very good thing. That fly ash is also diminishing. It's being sourced from storage ponds, but that's usually lesser quality fly ash. So and this is probably you guys are probably very aware of this, but cement is responsible for about 7% of the global warming potential in world industry. In a concrete mix, it's only around 10 to 12% of the mass of that mix. However, it's responsible for at least 80% of the global warming potential of that mix. And so that's why we're always looking at how do we reduce, either through lower strength concrete where we can use it, where we might be able to use less cement by, first of all, reducing the amount of concrete needed to begin with, reducing the over design of structure where we do need concrete. So there's a lot of kind of things that we can be doing up front before we even get to cement replacements. And then, as you heard earlier, especially in Chris's presentation, a lot of other things besides cement replacement that can and need to be happening in addition to cement replacement. But focused on cement replacement for a bit, glass is a material that we were using in concrete block for a number of years, going back 10, 15 years ago, and replacing, I think, about 30% of the cement in those blocks and performing very well. And so we started to talk about using that in ready mix concrete as well, because we know that there's a lot of glass available. Unfortunately, this graph is, you can see the blue bars are pretty stagnant. So the dark blue here is the amount of glass that gets recycled each year over the last number of decades. So we're not that great about recycling glass in this country. There are other ways to recycle glass. My favorite is refilling containers. None of us are able to do that super readily often at large scale. And so glass can also be, melted down and processed into new glass. However, this study that a colleague, Jordan Palmyre out in Oregon, and his colleagues did was very interesting because of the life of the material that it's getting recycled into. They looked at the global warming potential impacts of different end uses of recycled glass. And so this is ground glass pozzolan right here. And so you can see the negative, reduction in embodied carbon through putting the material into this use. So very close behind is reusing the container, but a lot of that has to do with the life of the material that you're putting it into. And, most concrete stays in place for a number of years as long as the performance and durability was carefully planned. So when we're working a lot right now with mixes that are about 40-50% replacement of cement with glass, and that's lowering the embodied carbon by about 40%. And just to very quickly to emphasize, it's not that glass is so much better than any other cement replacement. It's just that we're seeing it being a bit more future-proof. And so that's why we're especially focused on it right now. Slag is a bit higher in global warming potential. Fly ash is shown as 0 here, but this number is before fly ash was needing to be processed more, ground and filtered. So that number has evolved. But really the big thing is for cement replacements is to just replace the cement. Most of the impact comes from the grinding for glass. So through all this, we're looking a lot at, what we're looking at EPDs, we're looking at HPDs also. We wanted to be sure that when we use glass as a cement replacement, we're not creating issues for our labor force. This is amorphous silica, not crystalline silica. It's extremely important. So we looked at that very early on, and health product declarations in concert with environmental product declarations really give you that kind of full set of ingredients and considerations around impacts of those ingredients. And right now there are on the HPD repository more than 10,000 health product declarations. When this was first put out, I mean, think of it as a sort of a SDS on steroids. There's very little proprietary data on these. So there is sometimes, especially with liquid applied formulations, there tends to be more, but they're very transparent. So usually it's pretty common to see 97% and more that's fully disclosed on these. So and it's in a lot of different product categories now. So just very quickly, and to kind of wrap this up, just wanted to touch on the importance of the durability and the performance of any concrete that is used. It doesn't make sense to replace most of the cement in the concrete if the concrete's not going to last for as long as we want it to. And so this is just comparing some of the different cement replacements. You can see, when you have an all cement mix, you will gain strength earlier. And so we're trying to also work with our teams on, when do we really need a 2 or 3 day pour cycle? When can we go maybe a little bit longer? When can we look at 56-day breaks, maybe even 90-day breaks in lieu of 28-day breaks to make sure that we're using as little cement as possible to begin with, and then replacing as much of that cement as is sensible for the durability and performance. This has been another major benefit to the use of glass and concrete. The rapid chloride permeability is greatly reduced with the use of glass. And so when you go through freeze thaw cycles and the application of salts throughout the winter, the higher cement replacement with glass helps the concrete last a lot longer. And this is a pilot that we did with the Department of Design and Construction in, I think it was 2015 or 2016. So this was taken by Rich Jones there. And we've been looking a lot at urban heat island effect. So in addition to, climate considerations from the materials we're using in the operation of our buildings, also what, the surfaces around our cities, especially, and the vegetation, and how does that interact to create, certain temperatures in different zones. And disproportionately disadvantaged communities are far more greatly impacted by this. So you can see here the mix with the higher amount of glass is lighter. It's not like, I don't know if you guys have walked in front of the Grace building on a really sunny day. It's like, that's really, really bright. It's not quite that bright. Because we want to make sure that it's not causing not exacerbating other visual issues, but it does reduce the urban heat island effect. It is very similar to slag actually in color. And that is all I have to talk about today. Thank you guys.